Yeah.
Okay. Hi, everyone. I'm Federico. I'm a first-year PhD student at DESY Zeuthen. I'm gonna also talk about high-energy astrophysical neutrinos, but I'm gonna focus on the modeling of their sources. Let me quickly remind you what we mean by astrophysical neutrinos. We know that when high-energy cosmic ray hadrons hit a target of matter or radiation, they can produce gamma rays and neutrinos of high energies, and that's what I mean by astrophysical neutrinos. These have been discovered more than 10 years ago by the IceCube experiments that we mentioned today. And even though today we know there is a diffuse flux from the entire sky, it's hard to resolve the individual sources. So we still don't have a clear picture of what is the origin and the production mechanism of these neutrinos. Now, if we look at the history of this detection, the most promising class of sources is that of active galactic nuclei, or AGN. An AGN is a compact region that we find at the center of certain galaxies that emits photons over a very broad range of frequencies, and it can also emit neutrinos. From the scheme, you see a lot of names on the right part. That's because observing AGN, they've been found with very diverse properties, which led to a very rich classification. But today we understand them in terms of the unified model. They describe them as pretty much the same object, just seen from different point of views. So the classes that are more interesting for us are the one of Blazar and Cipher-2 galaxies, since are those that have been associated with certain neutrinos. So some of these sources have been associated with neutrinos. In particular, blazars are AGN that exhibit a powerful relativistic jet that points towards us, while Cipher-2 galaxies are more quiet galaxies with weak or absent jets. And the way we see them is pretty much on the same line of the dusty torus, so they are partially obscured. Looking more in depth at these sources, today we mentioned the Blazar TXS of 506 plus 056, that I would just call TXS. This has been the very first source to be identified with IceCube neutrinos, and it was identified as a neutrino excess during a gamma ray flare, as Maria mentioned. And due to this correlation between neutrinos and photons, people thought that they were created in the same radiation zone. And since TXS is a blazar, the most natural candidate was the powerful jet that they had. So to model the emission, the multi-wavelength emission, so in this plot, let me guide you through it if you haven't seen that. On the x-axis, you have the energy of the radiation. And on the y-axis, basically you have the amount of radiation that has been observed or is expected at those energies. In a jet model, high energy protons or hadrons are accelerated in the relativistic jets. They interact and produce high energy neutrinos. And historically, this is the way in which the signal from TXS has been interpreted. But then a few years ago, there was the detection of the Cipher-2 galaxy NGC 1068, which is actually the most significant spot in the neutrino sky. And the detection of neutrinos was not accompanied by a strong signal of gamma rays. So people believed that the production side of the neutrinos had to be what is called a gamma ray opaque source. So a source from which gamma rays cannot escape because they interact before. And the most natural candidate in this case was the corona of the AGN. The corona is an inner region of the AGN that contains a very dense field of non-thermal X-rays. These X-rays are both the target of proton interaction, so they produce gamma rays and neutrinos, but they're also the targets over which these high-energy gamma rays are absorbed. And this would explain the lack of gamma ray signal. Now, if we put things together, I told you that there's been detection of neutrinos from a jetted source, TXS, but then also detection from a non-jetted source. And this raises a question of how prominent is actually the jet for neutrino production. And in particular, if you look at the class of blazars, which both have a jet and the corona, where are neutrinos produced? So addressing this question, we focused on a specific scenario, which was the one in which maybe the neutrinos from TXS were produced in the AGN corona, while the electromagnetic radiation was still produced in the jet. To explore this scenario, we modeled the corona of the blazar TXS, and we treated as a spherical blob containing X-rays, accelerated protons, and magnetic fields. These three ingredients interact with each other, and the way they interact has been simulated numerically by means of the software AN3 up to steady state. So given this framework, we had to connect it with observations. So the first point to address was how much energy was available in the system. And this was actually a tricky point, because if you think about a blazar, when we look at a blazar, we are looking through its jet. So we cannot directly observe the corona. So what we did was look at direct measurements of emission lines and use known empirical relations between the lines and the power available through accretion. We estimated the X-ray luminosity of the corona in two different ways, and we treated these two scenarios separately, which are called what we see here as low luminosity and high luminosities. And we also treated separately the case of extreme luminosity that was specific for another flare that the source went through. What we found was that the X-ray luminosities were 1 or 2 Wagner magnitudes smaller than those observed from the blazar. So actually the electromagnetic emission was subdominant from the corona with respect to the blazar. Then the other point to address was how were cosmic rays accelerated in the corona? Because another point that we had to explain were the energies of the neutrinos that has been seen, which were up to the PeV energy. Given what we saw also with Maria, to observe neutrinos at PeV energies, we need acceleration up to 10, 20 PeV. And what we found was that this is possible if protons are accelerated by magnetic recognition, which is a process by which magnetic fields are rearranged and energy is converted from magnetic fields to the kinetic energy of protons. So that's accelerating. In all the three cases, this was giving us maximum proton energy, able to explain the neutrino energies from TXS. So having the three ingredients, the way to simulate interaction, the X-ray luminosity of the corona, and the particle injection for the primary cosmic rays, we simulated numerically the signal that we would have expected from the corona of TXS, and the results are in these three plots, which are relative to the low luminosity, high luminosity, and extreme luminosity. You see, again, with x-axis energy and y-axis amount of radiation, the solid black line is the electromagnetic radiation from the corona, and the dashed black line is are the neutrinos expected from the corona in the three signals. The color lines are the jet models in different epochs, and what you should be worried about is the red line with a red bar, which is the 10-year integrated neutrino signal from TXS. You see that the neutrino production from TXS, even though it can match the energies of observation, cannot explain the observed diffuse flux. And this leads to the conclusion. So throughout the study, we found out that the electromagnetic coronal X-rays is subdominant compared to the jet emission. And we also saw that the electromagnetic cascade initiated by gamma ray absorption is the only radiative signature from it. Then we saw that if protons are accelerated by magnetic recognition, the acceleration is fast enough to explain the energy of the neutrinos that have been observed. But however, the flux that would be expected is still orders of magnitude below the one that has been observed. So in conclusion, the neutrinos that we observed from TXS could not be produced only in the AGN corona, even though that there could have been a minor contribution. And this in turn suggests that for TXS and maybe for Blazar, the production in the Blazar jets is still a preferred explanation for the multi-messenger data. And that was it. Thank you.
Thank you, Federico. So for TXS, there was also this earlier episode in 2014.
Yes.
Have you also looked into that?
That's, yeah, sorry. I didn't spend too much time explaining, but this extreme luminosity is actually modeling the 2014 flare. So the extra luminosity that we chose was saturating the electromagnetic signal, and you see that the neutrinos still don't get there.
But so in the high luminosity case, you actually almost reached the neutrino level that you have here in terms of the red band, right?
Yeah, if you count for the error bar, yeah.
Yeah. I mean, there's also this thing called the Eddington bias that if you only see one neutrino, it's hard to estimate what's kind of like it could be like in the tail of a distribution, right? So
yeah,
it's hard to estimate what the actual flux
yeah.
level is.
Regarding the high luminosity, though, we took it as the most optimistic scenario, but it was already disfavored by energetics because we are talking about magnetic recognition in which there is expected an equipartition between the energy. And here, the amount of energy in protons that we assume for this most optimistic was a net eta p, which is a fraction of 1, which was already disfavored by peak simulations.
I see.
I didn't want to get too much into details, but the spectrum that we injected was following some results from peak simulations.
I see.
And also the parameters.
That was another question I had. Yeah.
Okay. Yeah.
Spectrum. Yeah. Okay.
It was a broken power law, breaking, I think so there was a hard spectrum up to tens of hundreds of TeV, and then we considered 2 different scenarios, decaying at e to the minus 2, e to the minus 3, depending on the guide magnetic fields. And yeah, and the important part that I wanted to address was the maximum energy that was dictated by the cooling loss. So we thought that the maximum injection energy was defined by the energy at which acceleration and cooling were the same.
Okay, thanks. Further questions? Yeah.
A very quick one. So is there any other non-jetted source besides corona? I mean, so you study jetted source, and so the non-jetted source you consider corona, right? Just
Yeah.
like corona. So so besides corona, is there any other non-jetted source?
Well, if you talk about AGN, I guess that maybe in some turbulent inflow, still close to the black hole, it doesn't have to be necessarily the corona. This was the most promising because it worked for NGC 1068.
So maybe I guess your motivation may be related to COVID-19, to COVID virus. Okay.
Okay, let's thank Federico again.